Students, so let us solve this problem. We are going to solve what is axial force, shear force and bending moment diagram for this particular statically determinate frame. Okay, so here it is called as statically determinate frame because if you see this particular support, it is a hinge support. Okay, and this is roller support. So hinge support is it can carry only two reactions. Okay, so it can resist force in vertical direction and it can resist force in horizontal direction. So first of all, let us just name the beam. Okay, let us name it as ABCD. ABCD. Now before we move towards solving this problem, let us understand that axial force is nothing but after calculation of whatever loads acting on each of the member. Okay, so whatever forces which is acting along the axis, so it can be, suppose if this is a member, so it can be tensile or it can be compressive. Okay, so if this force, it may be under tension, or it may be, suppose this is compressive force. Okay, so it may be under compression or it may be under tension. So that force we have to plot and that will be our axial diagram. Okay, then shear, after again calculation of reaction, what is happening at each and every section. Okay, so we will see what is the shear. Okay, this is across the section what is happening, that will be our shear force diagram. So similarly we will calculate shear force for this whole frame, and once we done with shear force, then we will calculate what is the bending moment. So bending moment means because of this loading, what is happening at some points, like important points, like here below the load, what is the moment, what is the moment here, what is moment at this connection point. So like this we will calculate moment also. So step number one is we are going to calculate for first reactions. So quickly let's see what are the steps over here. So we have to calculate reactions at the supports. Okay, the step number one. Once we calculate reactions, then we will draw the free body diagram, means we will simply disconnect this frame. Okay, this part number one and part number two, member number two, and member number three, we will simply draw them away and we will draw their free body diagram. Okay, we will separate them and draw free body diagram. Once we do that, then we will calculate equations of equilibrium for each and every member. So we will see what is the equations of equilibrium. So what are the equilibrium equations? It's nothing but summation of forces in x direction, summation of forces in y direction and moment. Okay, so that will once we get that, we will get all the required forces for each and every member. Once we get those forces, then we will be plotting them. So we will arrive at step number 4. So we can at a time go like this, like step number 1, then 2, then 3, and then finally draw the diagram. Or we can what we can do, we can do step number 1, 2, and for the third step only for each and every member. Suppose for first member only, we will first calculate all the internal reactions, then draw axial force diagram and shear force and bending moment for that. So that is also a really good way of completing the problem. So one by one each member we can complete, so that way we can do. So let's see here. Now here we have started with step number 1. Okay, calculate support reactions. Now for this particular frame, let us first name the frame. Okay, step number 1 is to name the frame, that is A B C D. So that is the frame name we can see. Now basic equations of equilibrium, that is summation of forces in x direction is 0, summation of forces in y direction is 0, and summation of moment is 0. So don't worry by looking at the frame and how we are going to solve. It's very simple. Every time you are going to use these three equations only. Why are you going to use these three equations only? Because currently we are solving a simple problem. Okay, statically determinate frame. So we call those only statically determinate frames where, okay, the frame which can be easily solved with three equilibrium equations. So we call it as determinate frame. Okay, now here let us use first equation. So summation of forces in x direction is equal to 0. Okay. Now here we can simply write by showing this arrow is here. So we can even show this arrow this side. Okay. There is nothing wrong if we show like this. So first when we consider what are the horizontal forces acting on this frame. So when we see summation of forces in the x direction is 0. Now here when we see this 20 is going towards right direction. So if HA also will go towards right direction, so it will become automatically we will get negative answer for this, right? Means if we say show it in this direction, so we can write HA plus 20 equals to 0. So we will get HA equals to minus 20. That itself shows that actually HA is not acting like this, but its real direction is this way. Okay. So we can get this direction and we can arrive at this particular answer. Okay, so we get horizontal reaction at A is nothing but 20 kilonewton. Okay, so we are done with summation of forces in x direction. Now coming to summation of forces in y direction. Okay, now let us see what are the forces in y direction. So for particular frame there are two reactions acting at the support, that is RA plus RD, and there is a UDL, okay, uniformly distributed load acting here, that is 6 kilonewton per meter. So when we write summation of forces in y direction, we can write RA plus RD is equal to 6 into 5. Okay. So this equation RA plus RD is equal to 6 into 5. So basically this equation we can simply write RA plus RD minus 30, right? This is going up. So this is minus 30 equal to 0. So when we do that, obviously minus 30 will go right side. So we will arrive at equation number 1. So that is our summation of forces in y direction. Now we got equation number 1. Now we should know what is the other reaction. So we can consider summation of forces about any one support. We can consider about D support, or we can consider about A support. So let us consider A support. So when we consider moment about support A, then what are the loads available? What all the loads available? So we can see that there is a reaction available, there is a UDL available, and there is this 20 kilonewton load available. So we will consider moment of all these forces about support A. Okay. Now whenever moment is there, let us assume clockwise is positive. It's up to you if you want to consider anti-clockwise positive. There is a full freedom. So it's up to own wish what sign conventions we want to consider. But whatever we consider, then be with that and don't change while solving the problem. Keep it consistent. Okay. So that answer will not be wrong then. So now moment about A is equal to 0. So this is for this particular A, this you can see that it is going upward, so it is making a anti-clockwise movement. Okay, it is making a anti-clockwise movement. So load into perpendicular distance, so I can write minus RD into 5. Okay, because 5 meter is a perpendicular distance. If this is a line of action for RD, so this is perpendicular distance, and we are calculating moment about A, so this is a perpendicular distance. So simple RD into 5, and that is going in anti-clockwise direction. So this is first part is done. Now coming to UDL. Now UDL, never do mistake here, it is kilonewton per meter. Okay, uniformly distributed load. So simply multiply with the span. So 6 into 35. So this meter will get cancelled. So it is total 30 kilonewton load, and it will act in the middle of the span. Okay, it will act here. So we will write 6 into 5. Okay, that is 30, and its moment about A. Okay, now this particular load is going in clockwise direction. Okay, it is going clockwise direction, so it is positive. So 6 into 5, and this particular distance is half of it, so that is 2.5 meter. So we will write this. Now there is only one load remaining, that is 20 into 4. Okay, so it is again making clockwise movement. So that we will write 20 into 4 is equal to 0. So when we solve this equation, we arrive at RD equals to 27 kilonewton, and once we get RD equals to 23 kilonewton, we simply substitute that value into RA, and when we substitute there, just see here RA plus RD is 30. When RD is 23, so obviously RA will be 30 minus 23, so we will get 7 kilonewton. So we are done with all the reactions at the support here. We have got RA, RD and HA. Now our step number 1 is complete. Okay, so step number 2. So to calculate step number 2, let us go to next slide. Okay, now here we need to calculate what are the internal reactions. Okay, what are the internal reactions? So in such case we need to draw what is the free body diagram of each and every member. Okay, what is the free body diagram? Means we simply free the all members, we simply free all members. Okay, so here our previous diagram, this is a actual diagram like this, we and then when we just separate all the members. Okay, so here we have we got this value, this is as 20 kilonewton. Okay, member AB is 20 kilonewton. Now when we have this 7 kilonewton, this 20 we have, this we have. Now we don't know what is HB here, that we will see, and we also don't know that MB will be in this direction or what direction. Okay, but simply we assume one direction of movement. Now when we have written this HB in this direction, so we will put HB, because this particular everything should be in equilibrium. So first though we will see just equilibrium of the individual member. Okay, and there should be equilibrium with the overall system also. So when equilibrium of individual member is achieved, then equilibrium of the overall system will also be automatically achieved. Okay, so here because I have drawn it like this, so if this is anti-clockwise I am drawing, so this I can draw the opposite direction. Okay, I will draw the clockwise, because finally at this point I don't know what is the moment and there should be a balance. So if I am drawing it like this, so I will draw this in other direction. Now if this is in this direction, so I will just assume it in this direction. Okay, so there should be, then this particular is beam is, it is also showing a sagging moment. Okay, so and this is a UDL. Okay, in this case similarly for this, because there should also be a equilibrium at this particular joint, so if I draw it in anti-clockwise, so I will draw it in clockwise. So initially I just draw what are the possible forces and moments. When we'll see every member individually, then we'll come to know. So here now we also have to decide that what is the what is the positive and negative forces we are going to get while calculating. So we have to assume that one person is standing inside. Okay, so when it is standing inside, so whatever we have to just assume that the person is standing, and the whatever forces at this side. Okay, uh, we have to decide that whatever compression, means that is our assumption, if compressive forces we are getting. Okay, so where compression will come, compression or tension, means I am talking about axial forces. So whatever compression if it is coming, means I can draw negative. Okay, so negative I can draw inside. Okay, so whatever negative forces if I am getting, I will draw that particular diagram inside the frame, and whatever positive I'll get, I will draw it outside the frame. Similarly for all the members. And then shear force, for shear force, suppose if this particular we consider it as a simply supported beam. Okay, then whatever force if we take any section, so if you see from this side, whatever force is going up, that is positive, and if it is coming down, that will be negative. Okay, so like this simply supported beam, we generally consider this sign convention. Okay, for shear force, this is the sign convention. Means if we start our calculation this from this side, left to right. Okay, when you consider start calculation left to right, just forget about this part. So when you start this calculation, so whatever forces going up is positive and whatever coming down is negative. But when you start calculation from left to right to left, then the sign convention is opposite. Okay, so for this particular case, it is, we consider it as positive. And then bending moment clockwise is positive and sagging is positive. Okay, so this is the sign convention we are going to follow. Now let us consider equilibrium of each and every member one by one, and we will simultaneously, for this particular problem, we will simultaneously calculate axial simultaneously draw axial force, shear force and bending moment diagram as well. So let us start with this particular member AB. So this is our particular member AB. Now here equilibrium of this particular member, everything should be in equilibrium. So what are the equilibrium equations? Let us see first what are the forces available. So summation of forces in x direction is equal to 0. That is our all time equation. So what are the forces here? We already have, anyways we have calculated that it is 20 kilonewton, we know, right? So when we calculate summation of forces is 0, so that is 20 kilonewton, we have already got the values. So this 20 and 20 is getting balanced over here only, okay? Whatever these forces, horizontal forces are getting balanced. That means we get the answer that whatever extra we wanted to, we kept it here to balance, there won't be any more force. So this BH becomes 0, okay? So here these horizontal forces we have balanced and it is in equilibrium already. Now let us see what is happening with the axial forces, okay? What is happening with the axial forces? So for axial forces, let us actually ideally we should start with axial forces only. So for axial forces, let us see what are the forces there. 7 kilonewton going upward and this by, okay, vertical force at the joint B. So it is nothing but by is equal to 7 kilonewton. So we are getting a compression, right? Compressive force. So we are done here. We know that axial force is nothing but it is a compression. So it will go in a negative side. Okay. So that is axial force. Then shear force, we know. We have just seen that shear force when we want to see what is the shear force, okay, in this particular section. So we can see that it is only shear force at A. It is 20 kilonewton, and suppose we write it as let us call it as F point, okay? So shear force at F is nothing but, we know it is 20 kilonewton, okay? So shear force at F and shear force at A, it is nothing but 20 kilonewton. So once we get the result, we have to simply plot the diagram. So this is our shear force calculation. Then bending moment calculation, okay? Bending moment calculation. Now we know that at support A it is a hinge support. So hinge support doesn't carry any moment. So we have to simply write down M at A is equal to 0. But because of this load, there can be some moment at this point, right? So we have to see what is the moment at this point and what is also the final moment at this point, okay? So let us see what is the moment at this particular point. So moment at point F is equal to, at this particular point it is 20 into 4, okay? It is 20 into 4. So we will write, and it is also going in clockwise direction. So 20 into 4, that is 80 kilonewton meter, okay? So for this particular uh, uh, member, moment at this point is 80 kilonewton meter. Now let us see what is moment at point B. So to calculate moment at point B, 20 into, okay, this load into perpendicular distance. So 20 into 5 and 20 into 1, okay, this is clockwise and this is anti-clockwise. So 20 into 5 minus 20 into 1. So 100 minus 20. 100 minus 20. So we get 80 kilonewton meter. Okay. So we get moment as 80 kilonewton meter. Is this value we are getting it as? So at both the places, at this point and this point, there is a same moment. Okay. At both the places, we are getting the same moment. Now let us draw axial force diagram. Axial force diagram, then shear force diagram, and bending moment diagram. So what is axial force diagram? It is 7 kilonewton. Okay, this is along the axis 7 kilonewton, and it is compression. So we will draw, suppose we said this is inside. Okay, this is, we have to draw it inside. So our frame is actually like this, our frame is like actually like this, and if this is the member AB, so we should draw it inside. Okay, so I am just drawing it, 7 kilonewton here. Okay, this is a straight line. Sorry for not making it perfect straight line. Okay, so this is 7 kilonewton, 7 kilonewton, 7 kilonewton. This is our axial force diagram. Now shear force. Okay, for shear force, this is we have drawn at the inside, so this is negative. Okay, so we need not write it negative, anyways we are drawing it inside, or we can show also negative because compression. So coming to shear force diagram. Okay, so inside is negative, right side is negative, left side is positive. So this 20 is going upward, so this is our positive diagram, right? Shear force we got it as positive. So let us plot here 20 kilonewton. This is 20 kilonewton here, we have drawn here line, and here also it is 20 kilonewton. So this is positive. Okay, so 20 kilonewton, and there is no shear force in this part because no force is acting, BH is 0. Okay, so this completes our shear force diagram, and you have to draw nicely with the scale in exam. Now in this on this tab somehow I am not able to draw a straight line, but in exam you have to draw a very neat beautiful diagram. Now coming to bending moment diagram. For bending moment diagram, there is bending moment 0 at this point, and we could calculate the bending moment as 80 kilonewton. Okay, at point F. So let us plot 80 kilonewton here. And then there is at point MB also there is a 80 kilonewton. Moment at A is equal to 0, moment at F is equal to 0, and then moment at B is equal to 20 into 5, and then 20 into 1, that is 80 kilonewton. So here it is constant. Okay, now here you can see that there is a relation between straight line of shear force, it becomes slanting line for bending moment diagram. Okay, so this is your positive bending moment diagram. So we have done with the first member of frame. Now let us move towards the second member of the frame. Okay, coming to the second member. Now for this particular case, BH value anyways it was 0 for us. Okay, and BY, we had a member here where our vertical reaction was 7 and 23. Okay, 7 kilonewton and 23 kilonewton. This is 0. This is 7 kilonewton. This is 23 kilonewton. There is UDL. There is this 20 kilonewton we have got, and there is a 20 kilonewton here. Okay, so this is our A, B, C, D. So when this is 7 kilonewton, we have received this also as 7 kilonewton. Now when there is this load 7 kilonewton, okay, so there will be balancing. There has to be balancing between two supports. So when this is 7 kilonewton, then this will be 7 kilonewton as well. Now when this is 7 kilonewton, then we can easily calculate what is Cy value. Okay, we are solving problem like this. Okay, so we have seen what are the forces available from this point, and we are trying to go like this. We can also do it reverse way. So here when we are going like this, so when 7 kilonewton and 7 kilonewton here for the member AB, okay, so that is balanced over there. So this 7 kilonewton is going down. So when we separate this member BC over here, so for this particular member, when it is going down, so this should go up. Okay, so this is our 7 kilonewton upwards. And the bending moment, what we got there as a 80 kilonewton, right? We got this value bending moment as 80 kilonewton here. When we got it as 80 kilonewton, so here also bending moment will be 80 kilonewton. 80 kilonewton meter, sorry. It is 80 kilonewton meter. So we got 80 kilonewton meter bending moment. Now we have this. Now we need to know what is the force at Cy. Okay. So what is the force at Cy? So here we have to simply see what are the summation of forces in y direction. Okay. When we see summation of forces in y direction, so we can write Vy plus Cy is equal to 6 into 5. Okay. This is UDL. So 6 into 5. So that is 30 kilonewton. Okay. So only two forces going up here, Cy plus By plus Cy. And By we know 7. So obviously Cy will be nothing but 23 kilonewton. Okay. So 30 minus 7. Total load 30 minus 7 is 23 kilonewton. So here we are done with our Cy force. Okay. This is 23 kilonewton. Now let us see what is the axial force here. So you can see BH is equal to 0. So for this particular case, CH will also be 0 to balance. Okay, that will be also 0 at this point. So we can write here for this, if we want to draw axial force diagram, if axial force diagram, so axial force will be 0 at this particular point. Now to calculate shear force, okay, to draw shear force diagram, we can see that for this particular case there is a shear force. Okay, only force we have to plot here. So at this point simply plot. Okay, this is your BC. Okay, this is your axial force diagram, first line, and third one is our bending moment. So at this shear force we will plot our 7 kilonewton here. 7 kilonewton. Okay, this is 7 kilonewton and this is 23 kilonewton. So it will be downward, 23 kilonewton. Once we draw this line, so we know for a simply supported beam we have solved the problems in second year. So because this is UDL, our variation will be a straight line. Okay, you have to connect this two dots. So I'm really sorry if I am not able to draw a straight line here. Okay, so this is a straight line. Please don't consider it as a curve. It is a straight line. Okay, so straight line, this is positive. Okay, and this is negative. So here if we consider this as a frame and if some person is standing over here, okay, so our shear force diagram we have drawn it like this, just to make you understand. Okay, this line is like this. Now what is bending moment? Okay, so what is the bending moment at point B and C, and what is happening in the middle? Because we know that wherever shear force is 0, bending moment will be maximum. Okay, so we know bending moment at B is 80. Okay, and we don't know what is bending moment at C. So let us calculate what is, first let us calculate what is bending moment at this particular point. or we can also calculate what is bending moment at C. Okay, so here first, to calculate bending moment at this particular point, let us consider this as a distance x. Okay, because we don't know at what point this particular bending shear force became 0. So let us find out what is this distance. So if this is x, this will be 5 minus x. Okay, so we can write, we can calculate what is x. X by 7 is equal to 5 minus x divided by 23. Okay, so when we solve this question, 23x is equal to 7 5s are 35 minus 7x. So if this 7 goes this side, it will become 30x. 30x is equal to 35. So with this we will get x is equal to, let me just check, it is nothing but 35 divided by 30, that is equal to 1.167. okay, so that is 1.167 meter. Okay, so our x value is 1.167 meter. So now we have to calculate what is bending moment at this particular point. Okay, so what is bending moment at any distance x, and that x is nothing but 1.167. So when we want to find out what is the bending moment at this point, which is 1.167, so we have only these loads. We have this vertical force, we also have moment, and we have the UDL. Okay, we will consider all the part of the left side. So we can write that 7 into 1.167. Okay, so this is clockwise direction. Even this is clockwise direction, only UDL will be in anti-clockwise direction, plus 80. Okay, 80 is a moment, so simply we'll count that, minus UDL is 6 into 1.167. okay, and it will act in the middle of this, so into 1.167 divided by 2. So our answer will be 7 into 1.167 is 8.169 plus 80 minus 1.167 into 6. So 4.085. So 8.169 plus 80 minus 4.085. 84.084. 84.084 kilonewton meter. Okay, that is a, when shear force is 0, that is the maximum bending moment. We got it here. Okay, so at this particular point we got this bending moment. Now when we see this last part, okay, CD, if we see, and if you want to also check what is the bending moment at C, so we can simply calculate. Okay, this is 80, and we can also check it here, what is moment at C. So moment at C is nothing but this load into perpendicular distance, 7 into 5. Okay, we are calculating moment at C. So 7 into 5 plus this moment is already there, 80. Okay, simply add all the moments, which is we are calculating moment about C. Then minus 6 into 5, 6 into 5 into 2.5. Okay, so these are all the forces we got here. So what is the total? Let's check. So this is 35 plus 80. 35 plus 80 is 115 minus 6 into 5 into 2.5, 75. So 115 minus 75, that is we get 40 kilonewton. Okay, so this is the answer we have got here. 40 kilonewton meter. Okay, this is the moment at this place. 40 kilonewton meter. So here we have drawn shear force diagram. Okay, we have done with the shear force diagram. So let us plot bending moment diagram. So as there is a less space, I am just drawing a line over here. So here this is 80. So let me draw here 80. Okay, this is 80 point because we have got MB is at 80. Then moment at C is 40. Okay, this is 40. We got it as 40 kilonewton meter, and maximum bending moment is 84.084. 84.084 kilonewton meter. Okay, everywhere you should write units properly. Now simply join these lines, end lines. Okay, and then plot a, this is UDL, so there will be a parabola. Okay, there will be a parabola for this particular diagram, and this is positive. So this way we have completed our bending moment diagram and shear force diagram for the second member. Okay, so we have done with this things, and now we will go for a third case. Now here in this particular case we can see that there is no horizontal force. Okay, there is no horizontal force, so this also becomes 0. Okay, and moment at C, what we have got here, uh, so we have seen that at x equal to 1.167 meter, maximum bending moment is 84.084. Okay, now what about moment at point C? Okay, moment at point C will be 0. Why it will be 0? Because this is this end, particular end. Okay, here at this point it is a roller support. Okay, so roller support cannot carry any moment, it cannot carry any moment. So at this point, okay, there is only one reaction, 23 kilonewton, only one reaction, and there is no horizontal reaction. Okay, so it cannot create moment at this point, so moment at C is 0. So it's simply, then we have to plot this all values over here. So for this particular at point B, okay, at point B our bending moment is 80 kilonewton meter. So we have plotted this point. So this is our 80 kilonewton meter, and maximum bending moment is 84.084 kilonewton meter. Okay, so how we have calculated? We have considered bending moment at this point. Okay, when we consider bending moment at this point, we are arriving at 84.084 kilonewton meter. So once we get this value, and because this is a UDL, okay, this is uniformly distributed load, so our bending moment variation will be a parabolic. So we have to draw a parabola. So this completes our second part of the beam. Okay, now let's see the third part. So here just have a quick okay, so we have got moment at B is 80 and this is 84.084. Coming to third part, so here at this case this is roller support at point D. Okay, this is our point D. So this is roller support. So our reaction is 23 kilonewton. So this will create, okay, axial force. This particular load will create axial force here. So this will also be 23 kilonewton. So our axial force diagram, it will be like this. Okay, this is, and this is compressive in nature. So we will write here 23 kilonewton, 23 kilonewton, and we will draw it inward. Okay, we are drawing it inward, means this is like this. We are drawing it like this. This is our axial force diagram. Okay, so we are done with axial force diagram. As there is no horizontal force acting, So shear force will be 0 and there is no bending moment. So even bending moment will be 0. So this is our third member. So we have done with third member. So let's quickly see what are the diagrams. Okay, so for first member our axial force diagram is like this on negative side. Then this is shear force and this is bending moment. Okay, then for the second case this is our axial force diagram. For this case this axial force is 0 here. Okay, so because this is also 0, so we are so this is for second member and this is for third member. Now let us gather all axial force, shear force and bending moment diagram together. Okay, so when we draw it here, so axial force diagram, so this is the A B C D. Okay, this is our beam, this is our frame, sorry. So for this particular frame our axial force diagram is like this. Okay, when we just combine all three members, so this is our axial force diagram and then this is our shear force diagram. Okay, so this is our positive side, this is out of the frame, this is also positive, this is negative. Okay, we have assumed that someone is standing here, so we have to see that all inside will be negative and outside will be positive. Similarly for this also, this is just to get an understanding. So these are the negative inside, and for bending moment also CD is 0 and the positive bending moment outside. Okay, so at this point it is 0 bending moment. So students, I hope now this problem is clear to you. Thank you so much. Hope you have understood. Thanks a lot. Problem part 2.